Module 2. In Module 2, we will discuss the define phase. Now, why define? The success of any Six Sigma project depends on proper definition of its scope. I myself have seen quite a number of projects failing in the long run because the scope has not been well defined. And proper definition of scope facilitates proper project execution and result in a timely manner. So definition of the scope is the first and the foremost responsibility of a Six Sigma professional when he or she starts with a Six Sigma project. The first deliverable that we do in a defined phase of a Six Sigma initiative or Six Sigma project is preparation of a project charter. A project charter is something like a project plan. It's a written document and works as an agreement between the sponsor and the Six Sigma project team regarding what is expected from the project. It's a live document and can be modified during the course of the project, at least till the analyze phase of the project. There are few elements or contents of a project charter. Starting from the left, the first one I will talk about business case. Now, for each of these, I will give you examples. Business case. Business case basically talks about in two or three small paragraphs. It details the detail of the Six Sigma project. What is the customer? What is my organization? What is the problem actually? And because of which we are doing this Six Sigma project? What is that we want to attain by doing this Six Sigma project? That will come in business case, ideally in two to three small paragraphs. The next block talks about the problem and the goal statement. Now, problem and goal statement should be specifically talking about what is the problem because of which we are doing a Six Sigma project and what is the goal that we want to attain. The goal ideally should relate to the upper and the lower specification limits or the CTQ that we had discussed in our earlier module. Next block talks about quite a few things. I will pick up something important. Project scope. Project scope is important. Suppose for one person from the HR department is doing a Six Sigma project. And in HR, as we know, there are several areas of work. Recruitment process, promotion process, increment process, payroll process, etc., etc. And if there is a Six Sigma project being done to improve a process relating to only the recruitment, the project scope should be clearly written that scope in is the recruitment process, scope out all the other processes of the HR department. So that would basically indicate what is the boundary of your Six Sigma project. The next area that I'm going to discuss is the milestone. What is a milestone? Milestone basically talks about the planned duration of your Six Sigma project, because whenever you are trying to do a Six Sigma project, there should be a planned duration based on which you want to start and you want to end it. So ideally, I could recommend you that whenever you want to define a milestone, just prepare one small Excel sheet with three columns. The first column, give the heading phases. Second column, give the heading planned start date. And the third column, planned end date. So in the phases, in 5 rows, you write define, measure, analyze, improve, and control. Against each phase, you put the planned start date and the planned end date. So that would indicate when you plan to start the project, when you plan to end this project. I have seen some people, what they do, they add two more additional columns to the Excel reports, actual start date and actual end date, which is a good practice, so that you can track against your planning. The last block talks about roles, people, expectations, and responsibilities. Now, a Six Sigma project is not a single person's job. It is a team effort. Ideally, a green belt or a black belt ideally will lead and execute a Six Sigma project till completion, but there will be other people, could be yellow belt certified or team members who are aware of the Six Sigma terms and terminologies. They will be working as team members from different cross-functional departments as applicable to help the green belt to complete that project. Business case, I will read out one example from a live example. Our customers of ABC project use online customer service and product registration website extensively to get the problems solved. This improves the customer satisfaction and also increases the revenue. It also reduces inbound calls to our call center. This paragraph sets the background of the project. Recently, it has been observed that the site availability and response time has deteriorated considerably, leading to customers' dissatisfaction and increased volume of inbound calls. So the problem thing is now coming up. A 5% decrease in availability could result in 200 more inbound calls per day, resulting in an additional cost of this much USD per annum. In addition, there is a potential revenue loss of approximately this much of USD per annum. So the problem and the difficulty we are facing in the process, that is clearly coming out, I said, in two or three small paragraphs. The problem statement, one example. Since April 2005, the customer service website of Amex project is down for average 2 hours a week during working hours. This is significantly higher compared to 2003 average downtime of 30 minutes per week. This negatively affects the customer satisfaction and cost on call center. So in one small paragraph, the problem statement is coming out very clearly, the specifically what is the problem because of which this Six Sigma project is getting done. Some examples of goal statement: improve website availability above 99% each day by January 2006. Improve quality of reconciliation output from 80% as of current to 98%. 98% here is the CTQ by December 2005. Whether you define a problem statement and more so a goal statement, it should be SMART. Now, SMART, I think all of you know, it's a very common quality management and project management term that we use, which indicates that whatever be your problem and your goal, especially I will talk about goal, which should be specific, it should be measurable, it should be attainable, relevant, and time bound so that you can, based on a specific time limit, you can complete your Six Sigma project. This is a sample project charter. As you can see from the left-hand side top, you have the project title. Then down, you have the business case, CTQ, scope in, then project completion target, problem statement, goal statement, scope out. Then you have the team formation, basis for project selection, customer, and also the VOC. So in one single template, you are getting the full details of the project. So whenever any person wants to start a project, from this, he or she can clearly understand and say, this is the purpose of the project because of which a Six Sigma project is getting done. Whenever you want to improve a process, an as is process or a current process, my next question to that person will always be, are you aware of your current process? If you are aware of your current process, then only ideally you can improve your process. So there is another quality analysis which is called SIPOC analysis: supplier, input, process, output, customer. So IPOC analysis basically On a high level, it maps the current process so that people can understand this is on a high level is my process. And based on this, we have to eventually improve our process. The total as is process, that is the current process, are divided into five entities, distributed across five entities. Who is my supplier? What is the input that the suppliers provide? What is the process that we do after the inputs are received from top to bottom in a hierarchical fashion? Only the high level processes. From the process, what is the output that we generate? And the output goes to which customer? So ideally, it starts with supplier, finishes off with customer. I will give you one example of the SIPOC analysis. This is one SIPOC prepared by the HR department. Now, the HR department has been addressed by the project managers that we need some specially skilled resources from our team. So, for them, the supplier are the project managers because they have provided the inputs. Input is requirement for new team members along with the skill set required. And after this, what HR does on a high level, one by one, HR gets the requirement. HR advertises for new recruitments. HR receives applications. HR filters the applications. HR calls associates for first round of interviews. HR calls cleared associates for final round of interviews. HR hands over offer letter to the selected associates. And eventually, from the last process, associates are absorbed in the organization and eventually handed over to the project managers. So over here, you see the project managers are playing a dual role, that is of a supplier and of a customer. With this, we come to a close of defined phase, that is module 2. Further discussion we will have in module 3. Thank you. Module 3. In module 3, we will discuss the measure phase. Now, the first thing which we want to discuss in the measure phase is a detailed process mapping. The current process, the as is process that you have, has to be detailed out with the help of flowchart symbols. Nowadays, everybody is aware of how to draw a flowchart and quite conversant with the flowchart symbols as well. So, with the help of flowchart symbols, you can very well draw a detailed process mapping of your current process, which ideally should have three components: value added activities, non-value added activities, and value enabling activities. Now, what is the value added activities? Value added activities are those activities which are recognized and approved by your customer and they are ready to pay you for this. Non-value added activities, value added activities examples are the production work that you do. The customer pays you for the final production services that they receive. So, all this production work that you do, for which your customer pays you, are the value added activities. The next activity, next component is the non value added activity. These are activities which are not recognized and approved by the customer and they necessarily don't pay you for this. Examples are rework, rectification work, correction work, damage control, all this. Value enabling activities includes those activities which enables more values to the products and services being produced, like training cost, which creates more skill metrics for the people, resulting in lesser defects going out to the customer, reviews and testing activities in a service organization, quality control, quality checks in a manufacturing organization, etc., etc. Now, as I said, that in Six Sigma initiative, planning has to be very, very strongly done, and in various sectors we will see several plans being made. So the first plan in a Lean Six Sigma initiative that we prepare is the data collection plan that we do in the measure phase. The data collection plan ideally includes what data to be collected, who will collect the data from within the team, and by what date the data has to be collected. And the most important area, what I will focus on, is the data source, identification of the data source. Like many organizations have data on some database, SAP database, Oracle database. Some organizations have some part of the data, at least with the customer, mostly in IT organizations. Some organizations have data on some tool. Some organizations prepares and preserve the data in MIS Excel reports. So you have to understand the authentic source of the data. And another area is how much data we should collect. That is how much sampling we should do. Now, the sampling as a concept is a quality management or statistical concept, I will say. It's a statistical concept, which I will say, whenever the total data, which is called the population data, is very huge and it might not be feasible to have the total data, that is the population data for our statistical analysis. So in this case, what happens? We take a representative sample, which should be ideally a random sampling. That is, take some from the top, some from the middle, some from the bottom. That is expected to give you a proper mix and match of the total data that we have. So the sampling will be done when the population or the total data is huge. In that way, we will be taking a data which is manageable from the total population. That is sampling. Now, whenever we do sampling as a concept sampling tool, there are many sampling tools that we have in the on the net nowadays, and there are three components which are necessary to do a proper sampling. That is, one is the population size, another is the confidence level, with how much confidence you are drawing the sampling. Okay, it can be ideally 95% confidence or 99% confidence also. Ideally, we do sampling with majorly 95% confidence. So you have to give three inputs. One is the population size, what is your confidence level, and what is your margin of error. Like a population size of 5,000 with confidence level of 95% and 2.5% margin of error means that your sample will always be 2.5% away from the population 95% of the time. So there is always some approximation done over here. And as you can see, for 5,000 population, the sample size is 1176. This way you can create your sample if required. Whenever we talk about statistics, we deal with three kinds of central tendency: mean, median, and mode. Mean is simple average. Median, if there is a number set which are arranged in the ascending order, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is median. 6 is the median because it is the central value. 5 digit on the left, 5 digit on the right. Mode. Mode. Suppose there is another number set 1, 2, 3, 4, 5, 5, 5, 5, 6, 7, 8, 9, 10, 11. Which number is appearing for the maximum number of time? It is the number 5. So 5 is the mode. In 99% of our statistical analysis that we will do, we will be by default using mean as the central tendency. Only in some very specific cases, we'll be using the median. Concept of variation. Variation is going away from the average performance. That is the deviation from the average performance. Ideally, whenever we talk about objectives of Six Sigma initiative, there are always two objectives. Number one, to reduce or remove defects or problems from the process and thereby improve the process. And the number two, to reduce variation from the process. We never said remove variations because variation in any process is inevitable. That's why we are having a reduction of variation. So variation in any process is inevitable, and it is our responsibility to bring the process stable to the maximum possible by reducing the variations and bring it more closer to the average performance. So more the variation goes away from the mean performance, it means that process is not consistent. These variations are generally of two kinds, common cause variation and special cause variation. Common cause variation are those variations which are always common, always present in the data, and special cause variation are the abnormal variations which are not always present, unexpected, unpredictable, and not a normal variation. Now, standard deviation is a term used in statistics which measures the variation. As I said, that in any process or data where the variation is less, that is the best data because that means it is more closer to the mean. Similarly, in any data where the standard deviation is the less, that is the best data, most consistent data. Now you see here two examples of Mr. A and Mr. B. Mr. A has a batting average of 53.9 and a standard deviation of 64.44, where batsman B has a batting average of 50.8 and standard deviation of 7.76. Which batsman looks to you as more consistent? Obviously, it is batsman B because the standard deviation or the variation is very less compared to batsman A. Now you see the data on the right. If you see batsman A performance, there is no consistency across. But in batsman B, there is always a consistent performance and all the results are closer to the average. Whenever we talk about data, there are two forms of data we generally consider. On the right, we have the continuous data, which is a measured data and can be represented in decimals, fractions, or percentages. Discrete data on the left are of two kinds. One is a discrete binary data, where there are two answers, good, bad, yes, no, right, wrong, married, unmarried, pass, fail, defective, non-defective. And another kind of discrete data is discrete count data. Discrete count, which is always a whole number, number of defects, number of calls. It can always be a whole number data. Now, normal distribution curve, it is very clear to understand that this curve is definitely prepared from a data which is a normal data. Normal data means any data which has only common cause variation, no special or abnormality in it. Okay. So if you see this normal curve, which is called a bell curve as well, the line at the center is the mean, and on the right we have one standard deviation, two standard deviation, three standard deviation, and on the left we have minus one, minus two, minus three. So between 1 and minus 1 standard deviation, you see 68.26% data are there. But as the standard deviation increases, the data is spreading away from the mean. That is what I said earlier, that the standard deviation should be, or the variation should be closer to the mean. More the variation, more the standard deviation, the data goes away from the mean, which does not look good and which is not a consistent or good process. Whenever we talk about normal data, there is a checking which we apply in normality checking. I will show you this normality checking in some subsequent modules when we work on this statistical analysis. Now, this is just as an example to show you there are two brands of data, brand A and brand B. Brand A data, the curve does not look like a normal curve. It's a flat kind of curve. And also there is a p-value, potential value, which is showing 0.007. In order to be normal, the p-value should be greater than 0.05. It is not. So we conclude that brand A is not a normal data. There is some abnormality in it. Similarly, for brand B, the curve looks like a perfect normal curve, and also the p-value is greater than 0.05. So we say that the brand B data is a normal data. Histogram and bar graph, these are part of intermediate graphical analysis. Both histogram and bar graph shows actually bars. Okay, but there is a difference. Histogram is ideally done with continuous data. It also shows an additional whether my data is normal or not. And it for each bar, it shows actually the frequency distribution between 0 to 15 how many, 16 to 30 how many, 31 to 40 how many, 41 to 50 how many. These are called frequency distribution. Unlike bar chart, it is done with a discrete data, and each bar ideally shows the exact number. Like over here, as you can see, how many are undercut, how many are oversized, like this. Minitab tool, we have already talked about Minitab tool earlier, that this is the most important and globally accepted statistical tool that we use for our statistical analysis in a Six Sigma initiative. This is the screen of Minitab, as you can see. At the top, there is the menu bar, file, edit, data, calculation, statistics, etc., till assistant. The middle part, the white part, is called the session window, where all the results of Minitab exercises or analysis that we do will be represented. And the last part, the worksheet part, which looks like an Excel, it is not an Excel, of course. Here, the data has to be input. The data input has to come over there. Whether you input the data manually or you copy the data from some Excel sheet and paste it over here, whatever, here the data will come. And based on the right menu that you select, your results will be displayed in the session window. Probability distribution. Probability distribution ideally means chance. The word chance means probability. So probability distribution means the chance of certain incident happening based on a given situation. Suppose you have a coin and you want to toss the coin. What is the probability percentage that you will get a head? It is 50%, because the other 50% probability is that you will get a tail. Now, whenever we have a continuous data, we do a normal probability distribution. Discrete binary data, we do a binomial probability distribution. And discrete count data, we do a Poisson probability distribution. Let us try to understand this case study from an educational institution. The time to certify engineering certificate is normally distributed with a mean of 40 days and standard deviation of 8 days. If the client wants that all the certificates shall be certified within 34 to 48 days, estimate the chance of meeting the client requirement. So here we understand that we have to ideally find out probability of 2 days. One is 34 and 48 separately. Then take a difference of the two, which will give us between 34 to 48. So this is the expression that is done for probability. P means probability, the last sentence. X minus mean, we try to find out how much is our average performance now away from the target, first target. So it is 34 minus 40 divided by standard deviation, which is equal to minus 0.75. But what does it mean, minus 0.75? For this, we will refer to a table which is called Z normal distribution table, where our value is minus 0.75. If you see, the leftmost column is Z column, and there is a value called minus 0.7. One digit before decimal, one digit after decimal will appear in the Z column, minus 0.7. And what is the second digit after decimal? 5. For this, we go to the right-hand side columns, which is headed by 5. So corresponding value from the table for minus 0.75 is 0.2266. Okay, but what does it mean again? Again, we have to wait and see. Similarly, for 48 also we calculate and your value comes to 1 or 1.00. In statistical, it is always worthwhile to calculate till 2 decimal points. So 1.00, you see, it is 1 over here. And for the next zero, I go to the column which is headed by zero. So zero. So it is showing a value of 0.8413. So for 34, we got a value of 0.2266. And for 48, we got a value of 0.8413. And we have to find out the probability between 34 to 48. Simply from 0.8413, I subtract 0.2266. I get a value of 0.6147. Convert it into percentage, I get 61.47%. So the conclusion will be that the chance or probability of meeting the client requirement that all the certificates could be given between 34 to 48 days is 61.47%. Whenever our data is a binary data, discrete binary, because we over here, the case study is we are talking about defective. On an average, 2% of the transactions processed are defective. On a particular day, out of 400 transactions audited, 21 turned out to be defectives. Is there a probability that the process performance deteriorated that day? That's what we have to find out. So, as because it's a defective option, it's a binary option, we always will do a binomial probability distribution. But for this, we need to have the data. So we enter the data on Minitab as shown. This is the data which is given by the organization. Then we select the calculation menu, probability distributions, and binomial probability. And after we get a binomial probability, we enter the number of trials, event probability, which is the average probability of defectives is 2%, so 0.02. Input column from the left, we select C2 defectives, double click, and optional storage where to store the probability is C2. After clicking OK, we get these figures, the probability figures over here, and then we convert it into percentage probability by taking the calculation option and the calculator first option. We change it to percentage chance. Okay. After getting this, if you see defectives up till zero, we get this figure 0.03 from this Minitab tools only. Up till 2, it is 1.31, and up till 20, it is 99.99%. That means what? Under the current situation, probability of having up till 20 defectives, it is already 100%. It is already 100%, 99.99. So unless and until there is a problem in the process, we cannot get more than 20. But on a particular day, we got 21. So the question was asked, is there a problem in the process that day? That's why we got 21. Yes, there is a problem in the process that day. That's why we got 21 as the process performance surely deteriorated that day. Our next case study will be on a count data. And whenever we have a count data, we do a Poisson probability exactly in the same way. The average number of repeat calls per day in a voice process is 20. On a particular day, there were 25 repeat calls. Is there a probability that there is a problem with the process that day? Same way, we enter the repeat calls data, which is given by the organization. This time we select probability distribution and Poisson probability. This is how we enter, as you can see over here, the mean and the input and the optional storage. Exactly the same we did the earlier exercise. We get this figures and then we put it into a table where you see probability of till 24 calls, it's already 84%. So probabilities of getting more than 24 calls will be 16%. So on a day we got 25. So it means there is no problem in the process. 16% of the time we can surely have more than 24 repeat calls. Measurement system analysis. Measurement system analysis actually means gauge R and R. The word measurements means gauge. Measurement system analysis applies when the same data is measured for validation or revalidation purpose number of times, multiple times by different people or by one people. Now, like probability, measurement system analysis results are also coming out in percentage. If in case of a discrete data, if the percentage comes to greater than equal to 80%, we will accept the result. In case of a continuous data, if the result comes to less than equal to 10%, which shows the variation, we will accept the result. Excellent measurement. If the percentage is between 10 to 30%, we have to take a call. That is, the organization management has to take a call whether we will go with this or not. But if the percentage is greater than 30%, we will completely reject and we will go with another round of measurement system analysis with a different data altogether. If you see this particular case study, there are six call IDs or six call duration which are measured by three appraisers two times. Ideally, all the figures should match, but only if you see only call ID 6 measurement has matched. So in a measurement system analysis, we try to find out in the course of measurement, is there a variation? And if there is a variation, how much of this variation is within acceptable limit? That's what we want to find out. Okay. And the acceptable limit I have already discussed for discrete data, it should be within 80% or more. And continuous data, it should be less than equal to 10%, which is excellent. 10 to 30, marginal, nominal, we have to take a call. And greater than 30%, non-acceptable. So this is one example we are doing. So that same measurement system analysis we are actually working out. We have input the data, call ID, appraiser, and the data we collect from the Excel sheet on which we do the exercises. We collect and put it in the on Minitab. Then we select statistics of menu, quality tools, gauge study, and gauge RNA study crossed. Whenever the same data is measured by multiple people at the very same moment, we go for a cross measurement system analysis. Then the part numbers we select from the left, call ID, operators appraiser, measurement data, data. And we select method of analysis X bar R because we want to check the mean and the range, that is how much is the variation. Click on OK. We get a value if you see total gauge R&R is 20.16. So this is the continuous data because this is the call related data, time related data. So here the gauge R&R percentage is 20%, 20.16, which comes within 10 to 30% range, 10 to 30% range. So 10 to 30% range. So we have to take a call whether to accept or not accept. Similarly, repeatability and reproducibility both are around 13 and 15 point something percent, which is also coming within the 10 to 30% range. So a decision has to be taken whether to go with this or not to go with this. The next case study, which is a measurement system analysis with discrete data. A project manager considered 10 transactions and chosen two appraisers at random for a gauge study. The transactions were evaluated on correct and incorrect basis. So clearly understood, this is a binary and discrete data. For all the 10 transactions, actual results are also available with the team lead. Two appraisers processed each transaction twice within a gap of 1 week. The results are as follows. Study the gauge R&R. So there are 10 transactions which both the appraisers Radha and Krishna have been asked to measure and give us whether they are correct or incorrect. And at the same time, there is always a standard previously defined. So they also want to ensure what are their measurement figures coming out correct or incorrect, and at the same time, whether those matches with the standard which is previously done. So what we do, we enter the data as you see on Minitab. Then we select the statistics menu, quality tools, attribute agreement analysis, attribute gauge RNR, and then we get this menu. In the multiple column option, we enter all the four appraisers, that is Radha 1, Radha 2, Krishna 1, Krishna 2. Number of appraisers should be 2, number of trials will be 2. Appraiser name, though optional, I would prefer to enter the names. So enter Radha space Krishna. And in the known standard or attribute, please select standard C2 standard from the left hand side. Click on OK, and then we will get the output onto Minitab. The first part showing within appraisers how much is the measurement system analysis. Radha's analysis is showing 70% accuracy, while Krishna's result is showing 80%. Radha has inspected 10, only matched at 7, while Krishna has measured 10 as well and matched at 8. Next, each appraiser versus standard. Against the standard, Radha has inspected 10, only 6 has matched with the standard, while Krishna's matching are 80%. One thing you notice that Krishna's performance has been steadily a consistently 80%. Next one, between appraisers. Between appraisers, they both have measured Between appraisers, they both have measured 10, only 4 have matched, so 40%. And all appraisers versus standard, the same result will come, it is also 40%. So one thing is coming out very clear that Radha's performance has been deteriorating gradually, and it is not close to 80%, whereas Krishna's result is always 80%. And we know that for a discrete data, the percentage should be greater than equal to 80%. Then only we will accept. So we will purely accept Krishna's performance measurement, but not Radha's. Process capability. You see, this is an uniform, globally accepted Six Sigma table, where you see from the bottom there is one Sigma, two, three, four, five, six, and there are defects per million opportunity. What happens in statistical term, defects are always evaluated based on per million opportunity. So when we are at one sigma level, we have a defect of around 6,90,000 per million opportunity on an average, which is around 69% defects. So that's why the yield, which is the good part, is around 31%. But one thing you notice, as the defect decreases, your sigma value is improving and ultimately reaching that level of 6 sigma, which is having 3.4 defects out of 1 million, which is having 99.99% yield, almost zero defect category. But one question is, how can defects go down in a process? Simple, by improvement to the process. So one thing we can infer out of this table, process improves, defects goes down, and your sigma value improves. That is what we need to ideally do in case of the concept of process capability. The concept of process capability simply means Concept of process capability simply means what is my current process capability compared to the target that we have to reach. For continuous and discrete data, both the process capability calculation are different. For continuous data, the process capability is calculated with a measure called CPK, which talks about the process capability index. For this, we first calculate CPU, that is process capability with respect to upper, and CPL, where we find out the difference of the mean performance that we have now from the USL and the LSL. And as because mean is at the center, USL, LSL on both sides, we divide it by 3 standard deviation in each case. And your CPK will be lower of the two. So your CPU value, say, if it is 1.53 and CPL comes to 0.57, your CPK value to be on the safer side should be 0.57 value. Similarly, for a discrete data, the process capability is calculated through a measure which is called DPMO, defects per million opportunity. CPK for continuous data, DPMO for discrete data. I will give one example now for the discrete process capability calculation. Suppose one of you go to one purchase department, just as an example, and you are required to fill up 10 forms. So the number of units over here are 10 forms, and each form has 15 fields. So opportunities per unit are 15 fields. So if I ask you how many are the total opportunities that you are filling up, it is 10 into 15, 150 opportunities. So my next question will be maximum while filling up, how many fields you can make a mistake? Maximum. You can make a mistake in all the 150 fields. But you are a very intelligent guy. So what you do, you made only 26 defects out of 150 fields. So your DPO or defect per opportunity will be 26 divided by 150. And what is DPMO? DPMO is DPO into 1 million. So 26 divided by 150 into 1 million comes to around 1,73,000 something. Now, for this CPK value of 0.57 and for DPMO value of 1,73,000, we have to go to the Z sigma value table to identify the ZST value, the second column from the left. 0.57, if you see my sample CPK was. Again, 0.57, if you go, you will see my Z value has been 1.70. Whereas 1,73,000 DPMO, it should be within 1,58,000 and 1,84,000. It could be around 2.45. This is how we have to find out that ZST value. Now, between ZST, there is also another column called ZLT, which is Z long term, and ZST is Z short term. Between ZST and ZLT, there is always a difference of 1.5 sigma because it is statistically proved that in the long run, if you don't improve your process after you calculate your process capability at that moment, it has been proved that statistically your sigma value will further deteriorate by 1.5 sigma. This is a generic thing. So, always when you want to showcase your process capability or sigma value, you will always show the ZST because the ultimate value is where we have to reach. That is the sigma value. In process capability index for continuous, there is another term which is called CP, which is called process capability potentiality. But we will always calculate the process capability index based on which the sigma value is arrived at. Also, there is another concept, PPK. PPK and CPK are basically the same, but the difference is PPK is calculated from population data and is called process performance, being the population data. And CPK, as we say, it is calculated from the sample data and is called the process capability index. One case study of process capability with a continuous data, the cycle time in minutes of each transaction in a day on both the ships was collected. The SLA for the cycle time of the process is 60 minutes. So that is the USL given. Okay. So cycle time, there are given, we have to calculate our process capability. So we go to stat menu, quality tools, capability analysis, and we select the normal option. Single column, we select the cycle time from the left. Subgroup size means if nothing is given in our analysis, that how many times the data has been calculated or measured, we will take it by default as one. So we have taken it as one because nothing is mentioned. Upper specification limit, we have entered as 60 because that is what has been given. And we click on OK. We get a CPK value which is equal to 0.77. If we go to that Z sigma value table, we will see corresponding value of CPK is 2.30 ZST. That is the value. But one thing, if you notice, CPU and CPK are the same. Why it is like this? Because there is no LSL which has been defined. So CPL is zero. So rather CP, there is no CPL. So there is no question of CPK being calculated as the minimal of the two. So it is always advisable to have CPU and CPK as the same, because the concept of minimal of the two CPU CPL does not arise over here. Another example of a discrete data process capability, the number of defective binary data. Defective tractors produced have been collected for a period of 1 year. The data is stored in columns, tractors produced and tractors defective. The maximum percentage defective we are willing to accept is 5%. Please determine the capability of the process. So we enter the two sets of data, tractors defective and tractors produced, and then we go to assistant menu capability analysis and we select binomial capability as we have a binary data. Then we select defective items, column as tractors defective, and column of subgroup size as tractors produced, because from within tractors produced, we are checking the tractors defective. Maximum percentage we give 5% as given in the exercise. And after that, we get a DPMO value 13573. So against 13573, if we go to that same Z sigma value table, we will see our DPMO will be 13573 and our process sigma ZST will be around 3.7. Around 3.7. This is the same Z table. We will now talk about something called yield. Yield means the good part, or the part against which there is no rework or rectification or defects. Yields mostly calculated in manufacturing organizations. The first one we will say multiple step yield. If you see, there are three steps in the table. First step, quantity bills in are 100, defectives are 5, defective bills corrected are 4, okay bills out are 99, step yield is 99% or 0.99. Similarly, for step 2 and 3 also, as shown, the step yields are 99% each. There is another yield which is called classic yield. Classic yield is calculated as the product. Classic yield is calculated as the product between multiplying the step yields of each step. So 0.99 into 0.99 into 0.99 equal to 0.97 or 97%. Next come to first pass yield. So total bills checked are 100 as an example. Out of these, first run defects are wrong name spelling 6, wrong address 3, wrong quantity 1, taxation terms not clear are 4. How many are total first round of defects? 14. So first pass yield is 100 minus 14 equal to 86%. Roll throughput yield or RTY. Roll throughput yield is calculated as a product of the fast pass yield of each step. Say step 1 fast pass yield is 86%, step 2 fast pass yield is 90%, step 3 fast pass yield is 95%. So 0.86 into 0.90 into 0.95, we have 0.73. So the roll throughput yield across all these three steps, rather of all these three steps, will be 0.73 or 73%. With this, we come to a close of module 3. Further discussions we will have in our subsequent modules. Thank you.